Alright, so for this next one, we're going to be tackling why a mismatch in the load impedance and the characteristic impedance results in reflection. Now, let's take a gander to another example. Imagine we had air. Alright, when we push a sound through the air, the the nature of waves makes it move, right? It makes it vibrate. And that's what sound is. It's just vibrations. Now, when it encounters a solid, some of that wave, yes, gets absorbed into the solid, but most of it gets reflected back. This is what we call an echo, right? So when we shout into a surface, it echoes back onto our ears. This is most noticeable when we're in a room that has only walls, no furniture yet, because most furniture can absorb sound, but walls are really bad at absorbing sound. They mostly reflect sound back. And the reason why is because of the change in medium, right? The air is, the medium of air is really sparse. It's a gas, all right? So waves travel through it very easily, but the kind of wave that travels through the air cannot travel that well in a solid like a block, like the walls or something. But when the walls have sound waves inside them, all right, yes, they can go outside, and when you hit metal, that's not metal. Yeah, when you hit metal, you can hear the sound of the metal. But most of the waves in the metal actually gets reflected back. And that's why when you hit metal, there's this vibration that's happening within the metal, like metal bars, or right? There's reflection that's happening all the time in the solid. It's just that some of the energy is released into the other medium. Now, why is this relevant? We can think of impedances as mediums, right? When ZO and ZL have the same impedance, that is exactly like having the same medium. So, for example, this is air, and this is also air. That means, in electrical terms, that means they have the same impedance, right? They are matching impedance. So when you send the wave in here, it sees no medium change. It sees no impedance change. And so it doesn't reflect. It lets it go through. However, when there is an impedance difference, when there's a mismatch, it can seem like there is a medium change, and therefore it will reflect back. And that's why mismatch equals reflection. Now, the degree of mismatch can be described using the standing wave ratio. The standing wave ratio in terms of impedances is ZL over ZO. But we have the condition that SWR has to be greater than 1. So we can include the additional fact that this can also be ZO over ZL. We can choose any of these two formulas, granted that the answer that we do choose is either greater than or equal to 1. Alright, so we can put this into the formula list here. We can put ZL over ZO or ZO over ZL. Now, we have that, and we also have reflection coefficient, which we can describe in terms of SWR. So SWR minus 1, so let's use ZL over ZO minus 1 over ZL over ZO plus 1, we get ZL minus ZO over ZL plus ZO. Now, since we can have ZO over ZL, this means that we need to take the absolute value for this part. So that is the That is the values of the reflection coefficient, formulas for the reflection coefficient and the standing wave ratio.